Hello, everybody. My name is Anyat, and today I'll be covering the problem number 3, identify sort. In part 1 of this question, we need to identify some characteristics of sequences that show the processes of different kinds of sorts. And let's imagine that we have the following unsorted list with the values 1, 3, 2, 5, 4, and 7. I'll use this unsorted list for the demonstration purposes. And of course, our ending goal is going to be to get all of those values in their correct spots. Now let's determine the behavior of insertion sort. We know that insertion sort works by using a very simple principle. We will compare the value at the current index to the one when it's left, and we'll perform a swap if the current value is smaller than the value on its left. Now, let's perform this algorithm on the unsorted list. We know that we can start from the index 1 because the value at the index 0 doesn't have any values on its left. Let's compare 1 to 3. We know that 1 is smaller than 3, therefore we don't need to perform any swaps yet. However, when we reach the index 2, we know that 2 is smaller than 3. Therefore, we need to perform a swap. And after a swap, we get the following list. We will have 1, 2, 3, 5, 4, and 7. However, one thing that you should definitely notice is that insertion sort doesn't finish after performing a swap. We will still be working with the current value until we make sure that the value on the left of the current value is actually smaller than it. And here, 2 is larger than 1. Therefore, we're fine. We can go to the next iteration. And on our next iteration, we have the value 5. And we know that 5 is larger than 3. Therefore, we're fine. And we will repeat this process over and over again until we get the sorted list. Here, you should definitely notice one very important pattern. So the value 5, 4, and 7 will remain unchanged for a very long time because insertion sort works by changing only the values that are on the left of the current value. Therefore, it is its most important and prominent property. We can describe it by saying the values at the end of unsorted list will remain in their original spots for a very long time. Now let's go to our next sorting algorithm. Selection sort is one of the very useful ones, and it works by a very similar principle to insertion sort. So insertion sort and selection sort have one very important difference. Here, in a selection sort can switch to any value that is on its right, and insertion sort must switch to the value on its left if needed. So let's run selection sort on our unsorted list. We will start from the index 0. So we know that 1 is smaller than every value on its right, and it's in its correct spot. Therefore, our selection sort will go to its next iteration. So if our current value is 3, we will compare it to every value on its right and try to determine if there are any smaller values. So we know that 2 is smaller than 3. However, our selection sort won't stop when it reaches this point. It will keep going and compare it to the values 5, 4, and 7. And when it makes sure that 2 is actually the minimum value, it will perform this swap. So the difference between insertion and selection sort is that our current value can be switched with any value on its right. So let's write this property down. Selection sort is very famous for um, sorting from the start. And by that, I mean that the values at the front will be sorted one by one. So the values will start appearing at the start of our array one by one in their correct order. Now let's go to heap sort. When you're dealing with heap sort, you should definitely remember that at 61B, we use max heaps in these types of problems. Therefore, a max heap will always transfer the largest value to the front, and after that, we will pop the largest value, and it will be at the end of our sorted list. So let's write this down. The largest value will be at the front. After that, of course, the second largest value will be at the front, and etc., until we reach the final state. Merge sort is one of the harder ones to identify for certain. So it's best to start by eliminating some other options. However, merge sort also has its own characteristics. So let's copy our unsorted list. It has the values 1, 3, 2, 5, 4, and 7. So 1, 3, 2, 5, 4, and 7. Here, you should definitely remember that you need to make one line, and the values from the first half cannot get to the second half. This is one of the very prominent qualities of the merge sort, and those two halves get sorted on their own. Therefore, you can approach merge sort by identifying groupings and seeing if they got sorted on the next iteration. And finally, we have quicksort. Quicksort works by choosing a pivot. So if you can find an element which will be larger than every value on its left, but smaller than every value on its right, you stumbled across a quicksort. So let's run quicksort on our unsorted list. So we'll choose 2 as a pivot. It's usually the value on the middle. So we'll put 1 here, 2 here, and 3, 5, 4, and 7 on its right. So every value on the left of our pivot is smaller than our pivot, and every value on its right is larger than our pivot. However, you should notice that 5 and 4 are not in the correct order. Therefore, our list is still unsorted, and we will run quicksort on this half. So in quicksort, you need to check from left to right if there is a value that is larger than every value on its left, but smaller than every value on its right. Now let's approach the part 2. Each of the following sequences represent an array being sorted at some intermediate step. We need to match each sample with one of the sorting algorithms: insertion sort, selection sort, heap sort, merge sort, quick sort. We also are given the original array, which has the values 5103, 9914, and until 4411. The first line is a bit different from the second line. Let's identify the sorting algorithm that was used here. So let's first of all notice what has changed. So 5103 has switched its spot with 3715, and now 9914 is also has switched its spot with 6035. Here, this half is sorted. We know that each value here is in its correct spot, respective to its half. However, 9914 is smaller than 2261. Of course, that means that there is some sorting left to do. And this is a very clear sign for merge sort because one half got sorted correctly. Therefore, we can immediately put merge sort here. Now let's go to the part B. So in part B, we have used selection sort. How did we identify that? First of all, notice that every value is appearing on its correct spot, starting from the left, or you can also say from the front. So 0608 is now at the start, and 1163 is also now at the front. So what has changed from the first sequence to the second sequence? We notice that the value 2261 is now on its correct spot. And it has switched from here to here. So it has switched from not its neighboring index. And every value is in the same spot. And this is a sign for selection sort, because in selection sort, we said that the values can jump very big ranges compared to insertion sort. Now let's look at the part C. So here you need to notice that the largest value is now at the front. And at the second sequence, we can notice that now the value 9797 is actually at the end of our array. Therefore, it is a clear indicator of heap sort. And lastly, we have either quick sort or insertion sort. So here we have used quick sort in part D. You can notice it from just considering every value. So let's begin from 5103. You need to check if every value on the left of 5103 is smaller than 5103. And of course, it's correct. And now let's compare 5103 to every value on its right. However, here, we notice that there is 608, which is smaller than 5103. We'll do the same with 6008, and we know that immediately it's not our pivot. And 37015 might be a good option. However, it's smaller than, it's actually larger than the value on its right. Therefore, it's not a pivot. 2261, same, not a pivot. And you'll continue this process until you get to 6035. And you can definitely notice that every value on its right is larger than 6035. And every value on its left is smaller than 6035. Therefore, it is our pivot. To make sure, you can analyze the second sequence too, and you'll notice that 3715 here, it was our pivot. And every value on its right is larger than 3715, and every value on its left is smaller than 3715. Our last two sequences are very similar to each other. So we have noticed that the values at the end are on their initial spot. And our array is getting sorted from left to right. And it's a clear indication of insertion sort. Thank you for covering this problem with me.